probably not the most important lesson, but probably something you haven't encountered before. And it's so crazy foreign that we need to talk about it. Let me read this to you. This is from a sample exercise that was published in 2014 and has since popped up twice on the AP test. How could the variables used in part A be graphed in order to determine the acceleration of the block using a best fit line? Now, I have to mention that because you've probably never encountered something like this before, and if you had, good on your math teachers. But let's talk about this general idea of taking data and graphing it so the slope can be a value you're looking for. Okay. First of all, what is the form of a straight line? What is the form that you've been taught since 8th grade for a straight line? Good, yeah. So the formula that we like to use is y equals mx plus b. Y is what we call the dependent variable, the thing the lab gives us. Okay. X is the independent variable. That's the thing we're changing. Yeah? What is m? So important, we're using a different color. M is the slope of the line. And what is? It's pink. It's fuchsia. It's kind of a purple. And what is B? The y-intercept. It's where the line crosses the y-axis, right? Where the line crosses or intercepts the y-axis. Okay. Now, I have up here, I just found this morning. I was going through some old gear. I have up here, quite possibly, the oldest spring scale that's ever been known to man. It's super, doesn't have any calibration. It's just a spring on the back and then a scale. And it's a pretty hefty spring because if I put a 1 kilogram mass on here, it only goes down part way. There we go. It goes down part way. But it went down some distance, right? Now, if I put a less massive weight on it, it's going to go down less distance? Yes. Okay. And that's given to us by a law. And what is that law? Anyone remember? Hooke's law. Exactly. It's Hooke's law. So Hooke's law is, my beautiful blue pen is just about done. Oh well. Hooke's law. And Hooke's law has the formula negative x equals k, or negative f equals kx, or f equals negative kx, depending on what textbook you look at it. Okay, it's one of those two things, depending on how you look at it. In other words, the restoring force, F, is given to us by the spring constant multiplied by the extension distance, or the displacement. Make sense so far? So what is typically done, and I'm not doing it because it's just too easy for you. What is typically done is you hang masses from a spring scale and you measure how much the spring scale thing moves in distance, or just any old spring. And you might get data that looks like this. If you we'll measure force, which is Fg, and then x, which is extension. If you put a 10 Newton force on there, it might extend 0.2 meters. And if you put a 15 Newton force, it might extend 0.25 meters. And if you put a 30 Newton force, it might extend, actually this should be 0.4 meters, 0.6 meters. Okay, see how this is going? The general idea, which is 0.3, sorry, 0.3. There we go, 0.3. Oh, I got it. I'm just coming out of the numbers out of my head. You get the general idea how this works? And if you put a 40 Newton force on it, it should extend about 0.8 meters. Get the general idea? Okay, so you can use this information to create a graph. So, what variable do you want to put on the x-axis? The Fg. Okay, the Fg. And what variable do we put on the y-axis? Do you want to flip them? Yeah. Okay. Even though you are changing the weight, you kind of jumped ahead a couple steps. Even though you are changing the weight and measuring the displacement, we can flip them. We can put the Fg on the y-axis and the displacement on the x-axis. And if you did, well, like 0, 0.2, 0.4, 0.6, 0.8, 1.0, and this will be 0, 10, 20, 30, 40, 50, and so on. Okay? And when you graph them that way, at 10 we have 0.2, at 15 we have 0.3, at 30 we have 0.6, at 40 we have 0.8. You graph them that way and you get a line that looks like that. And it has the formula y equals mx plus b. You bored yet? Oh, just wait. Okay. So what is the y in this case?
The weight.
Yeah. Y is our fg. What is the x in this case? Displacement, by coincidence, is still just x. And then there's the m. This is the m. What is the m in this case?
The spring constant.
It's the spring constant. Okay. The f is a spring constant. So, creating a graph of your data will give you, yeah, the O that just kicked in. Some of you are like, aha. Creating a graph of your data of y versus x will give you a slope that is equal to the spring constant. So when you graph it all and it gives you the value of your slope, that slope is the spring constant. Does this make sense? Okay. Now, you actually already manipulated a little bit of data because you took what should have been the x and made it the y, and what should have been the y and made it the x. You can do this with almost anything. And this is what the AP wants you to know how to do. In your data, in your lab, you used spring data that has the formula T equals 2 pi the radical, what over what? M over K. M over K. Can you graph this in such a way that the slope can be used to find the spring constant? Got a pretty goofy equation here. Now what you measured was the period. So the period is what you measured. You measured this. And you changed the mass. And you only have one other variable in there, and that's a spring constant. But because it's a spring constant, it's a constant. So you have one thing that changed via something else, and everything else is a constant. So you can rearrange this equation so the slope can be given to you, or can give you, the spring constant. You can do it. Now, let me show you something really, really goofy. The y value and the x value do not have to be their own numbers. They can be a little bit of functions too. So let's change this into something that makes some people itch less. Let's get rid of the radical. If you wanted to get rid of the radical, what would this equation become? T squared. Good. It would become T squared equals 2 pi squared. Okay. And then m, and you want to do m over k instead of m times 1 over k? All right, that's fine. You can do that. Times k. So some of you are like, oh, good, the radical's gone.
It's all over k or just the...
Well, it's commuted. I mean, you want it 1 over k and m over k just like, you want to do it that way instead?
Yeah.
Yeah. You could also just do m times 1 over k, but either one works fine for me. I'm comfortable if you're comfortable. Okay, so far so good? Now, how do we put this in the form? Our goal, our ultimate goal is y equals mx plus b.
I'm just really confused because you said you're trying to see how we can get the spring constant from the slope. But right there it says k is the slope of this is also the constant. Right?
No, I'm not saying it is the slope. I'm saying we want it to get to the slope. Our goal is to get the slope. It's not the slope yet, but our goal is to make it the slope.
Okay.
Anyone else have any ideas? Anyone have any ideas?
Side by K.
That's a great idea. So we're going to go T2 times K equals 2 pi, that quantity squared, m. Are we getting closer and closer to y equals mx plus b? What's next? We're going to definitely do something. We're almost there. Can I give you a little bit of a hint? Do we have to write this y equals mx plus b? Can we also write it mx plus b equals y? Why not?
Just subtract the whole thing?
We can't subtract because there's no addition or subtraction in the formula, so we have to use multiplication and division.
Divided by 2 pi squared.
Great. So now we have t squared, k, I'm going to do something like this. I'm going to go 2 pi squared in the bottom and put it in parentheses equals m. Which is mass, not slope. What we have now, this formula allows us to graph data where the slope can be used to find the spring constant.
Wait, that's it?
That's it.
That's not.
I know it's weird and it makes you itch a little bit, but the AP wants you to learn this, and every time you get something like this, the points are really, really easy to get because you're going to have a whole bunch of students globally who've never seen this before. And they're like, I can't graph that way. That doesn't work. Oh, yes, it can. And we're going to do it in a couple times the rest of the school year before we get to the AP review. So what thing here is the x? Be careful. Yeah. This is the x.
Why?
And this is the y. Because this is written in y equals mx. There's no plus b in this case. It's just y equals mx.
Oh.
Okay? So you're going to put, you see it in your mind's eye? You see how we basically took the y equals mx plus b and flipped it around? So it's y equals mx. Okay. I can see the steam coming out, but I'll draw a nice little bow around it here in a second. So if you graph, yeah, you're like, my brain's warming up. If you graph your data as T2,
T2 or T squared?
T squared, thank you, T squared, and you graph T squared versus mass, you're going to get a line that looks like this. And its slope will be k over 2 pi squared. So whatever you get for the slope, when you divide it by 2 pi squared, you'll get your spring constant. I'll say this again.
If it's the slope, you have to multiply it by 2 pi squared.
Like I said, if you take the slope and you multiply it by 2 pi squared, you will get k.
Okay, that's...
Okay? Does this idea make a little bit of sense? And this is what the AP wants you to know how to do. Taking data that is all goofy and rearranging it so you have a single number that you can extract the slope from. No variables. But Mr. Byers, you graph something according to period squared. I know. It's strange. And in 2009, they threw such a curveball at you, you actually had to graph the 1 over x, not the x. I know. But you can still do that. Okay. So I know you're totally confused, and that's probably 80% of you are confused. But let me just talk about why this is important. The AP wants you to know how to extract data from, or extract a data from a big data set. and be able to rearrange equations so you get the formula y equals mx plus b. Our original equation that we used with our inertial balances was t equals 2 pi the radical m over k. If you graphed period versus mass, which most of you did, you're going to get a graph with a crazy slope. And the slope will have a 1 over in it. And the m will have a 1 over in it. So to take care of that, you square everything to get rid of the radical. When you get rid of the radical, the formula becomes 2 pi, or t squared, equals 2 pi squared m over k. Now, you can graph it like that, but then the slope will be 1 over k, which is not all that much fun. You don't want an inverted slope. In fact, most of you found your graph. What did your graph, when you graphed t versus mass, what did the slope look like? It looked like that? It should not have. Because when you graphed your period versus your mass, as your mass increased, your period did what? It should have looked something like that.
I did the line with best fit, it just did a straight line.
Oh, because the points were really close together? Yeah, what you got was this.
Yeah, it looked like that.
Yeah.
So, did I do it wrong?
No, it's just because your points were so close together that you only got a small chunk of the curve. If you graphed it as 1 over x, you should have actually got a value for your r value that was actually better than the straight line. But I didn't want you to do that yet. Okay, so take a look at this. I know this is confusing, but I'm introducing it now. We'll use it again in a couple times. Okay, so when you did this, and you took k, you basically have y equals mx plus b. Only this is going to be your x, this is going to be your y, and your slope is going to be k over 2 pi squared. So,
Wait,
yes?
why is t squared x? Why can't the other thing be x?
It can, but then you will have a slope that is 1 over k, because you'll have this situation. If you make this y and this x, your slope is going to be 1 over k.
Why can't you make the bottom, why can't you, that is x, and then the t is m. T squared is m.
No, sorry, you meant bottom.
Like, on the left side, why is it that that has to be m and the other one, and the t squared has to be x?
Because your slope is attached to the x value. Your slope is going to be attached to x, so you get a positive slope that you can manipulate. Okay, does that make sense? A little bit? So you have in your lab, I'll answer a question in a second. Yeah. You have in your lab where it says part 4, rearrange the equation, advanced placement level. Rearrange the formula for period versus mass to create an equation in the form of y equals mx plus b with k as the slope of the line. Use the data you graphed earlier, apply the rearranged equation to the slope of the line created in the graphical analysis, and compare your spring constant found in this manner to the spring constant you found in part 3.
So, people turned in.
It's still in the box. No. You did part 3 right. You just plug the numbers in to get your spring constant. What I'd like you to do is with the remainder of the time, I'd like you to graph your t squared versus your mass. T squared as the independent variable, mass as your dependent variable, and your slope will be given to you as k 2 pi squared. Use that number to find your slope and see how your slope compares to plugging numbers into your value to get slope. Okay? Yeah. You mean multiply 2 pi squared by t squared? Uh-huh. And that's what you do for part 3. Yeah, that's what you do for part 3 to find the spring constant. Okay, so work on that, pick up everything else, and finish up the lab, and then we will see how we are at the end of class.